All right, my dear children of class 11 science, as I said already, we learn a very important law known as Wien's displacement law. Now, this is actually a law related to a topic called black body radiation. So, as far the radiation term is concerned, they are the body which can completely emit the radiation, and there are the body, which completely absorb the amount of radiation falling on it. And such type of body, as you have learned already, is called perfectly black body. That's why perfectly black body is one which absorbs completely all the radiation falling on it, whatever the wavelength is. And perfectly black body is also a body which emit radiation, of all the wavelength, which emit radiation from it with all the wavelength. So that's why you know that black body, which is a good absorber of heat, is also a good radiator of heat. So perfect black body is a perfect absorber of heat, and it is also a perfect radiator of heat. So remember this part also. But it doesn't mean that for perfect black body, it should be essentially seen as black. It should be appears as black. Like I gave you the example last time in one of the video that sun is also considered as a perfect black body, but it doesn't look black. But as per the concept of theory of exchange, you learn, children, that a body can emit radiation. Any body can emit radiation. But especially when we define Wien's displacement law, this law is basically meant for black body. Black body and the radiation emitted by the black body at different temperature. And it emit radiation of all the wavelength. It emit radiation of all the wavelength. So for this case, two scientists named Lummer and Prinksheim, in the year 1899, they observed, so this radiation emit from a black body at different temperature. So as I said already, a perfect black body is a full radiator of heat, which means it emit radiation of all possible wavelength. So with this concept, with this consideration, as I said, Lummer and Prinksheim, in the year 1899, studied about the distribution of energy. But what distribution of energy? Spectral distribution of energy produced by the black body. Black body. Now spectral distribution of energy means energy distribution among different wavelength. So try to understand. Spectral distribution of energy means energy which is distributed among different wavelength in the radiation coming out from a black body, and at different temperature. So for that they use some electrically heated chamber and all, and they perform some experiment. So from that experiment, they observe that at different temperature, the radiation emitted by the black body, have a different energy which emitted. And this energy which emitted, is expressed by the graph or curve we called, and this curve is also called distribution curve. Energy distribution curve based on wavelength. So these two scientists, Lummer and Prinksheim, heated that black body, as I said already, to different temperature, and they drew a curve as a curve called a distribution curve for different temperature. But they drew the curve at the same graph. And this graph, this particular curves which we obtain on the same graph have the same shape, almost have the same shape. But for different temperature, the distribution of this curve as a form of energy with respect to wavelength. So children, remember this part. The graph which they plotted is actually based on energy and with respect to wavelength, energy versus wavelength, at different temperature. So as per the curve which was found on the same graph, this curve whose general shape was same for all the temperature, had given lot of information, and it gives the characteristics of black body. So I'll draw a graph which was plotted by these two scientists, with respect to the energy, and the wavelength at different temperature. So the graph nature was shown like this. So I'm showing the graph which was plotted as the energy, with respect to the wavelength. Energy with respect to the what? Wavelength. So this graph which was plotted had a nature like this. Okay, let me just show you the nature of the graph. Okay, so first let me draw the graph, then I'll explain it. Okay. Okay, so the graph which I plotted has a nature like this, and this is the graph which is plotted at different temperature. Let me consider the first graph which is at temperature T1, second graph is at temperature T2, and third graph is at temperature T3. Now I consider out here that T3 is greater than T2 and T2 is greater than what? T1. That means when you move from this lower portion graph to the upper portion, so this graph nature changes, okay, means is shifted to the side, okay, where the temperature what? Increases. Okay, and this is actually for energy, okay, versus energy E lambda with respect to the wavelength, and that is produced by the black body radiation. Now the graph plotted by this Loomer and Pringsheim was observed by one of the great scientists, okay, whose name is Wien. Okay, now this scientist, this particular scientist observed this graph and make some conclusion with respect to the energy which can be emitted by the radiation, okay, energy emitted in the form of radiation from a body in terms of what? Wavelength, okay, at different temperature. Okay, so as from the graph observation which was made by this particular scientist, it is found that it was made the observation that at a given temperature, at a given what? Temperature, at a given what? Temperature with the what? Increase, with the increase in what? Wavelength, with the increase in what? Wavelength, and that wavelength is say lambda, okay. The energy, you can see the graph also, the energy that is E lambda, okay, first you can see increases, you can clearly see in the graph also, it first increases, okay, reaches to a what value? A maximum value, reaches to a maximum value, and then you can see it is decreasing and then decreases. So the first observation is at a particular temperature, okay, if you see a graph between E lambda and lambda, okay, E lambda, the energy, okay, first increases, okay, reaches to the what value? Maximum value, then after it decreases, after that it decreases. This means that for a given temperature, the energy and which emit from the black body is also called radiant energy, and this radiant energy energy emitted by the black body become maximum at a particular wavelength, and I consider that wavelength is say lambda m, and this wavelength is also called dominating wavelength. Okay, sometimes we also call it dominating wavelength and the peak value of the wavelength. Okay, so this energy become maximum at a particular wavelength. Say at this particular wavelength, at this temperature, the energy become maximum. So say at a temperature T1, at this particular wavelength, the energy become maximum. Okay, so from this, as I said already, at a given temperature, I write down for a given what? For a given temperature, okay, the energy that obtained from this black body is also called what energy? The radiant energy. What energy? The radiant energy. So the radiant energy emitted, okay, by a black body, black what? Body is maximum. Energy become what? Maximum, okay, for what wavelength? Particular wavelength. For a particular what? Wavelength. For a particular wavelength, and that wavelength is marked by letter lambda m. Okay, so that most of the energy emitted lies in this wavelength only. So remember this part, children, that when black body emit radiation, it emit radiation of all the wavelength, all possible wavelength, but that particular wavelength only in which the energy emitted become maximum. Okay, and that emitted energy become maximum at that particular wavelength, and that wavelength is called maximum wavelength, also called as dominating wavelength. Okay, so as for the observation made by this Loomer and Prinksim, so this particular scientist Wilhelm Wien made this conclusion. Made this what conclusion? But this is not. This is only true for a particular temperature. But when the temperature changes, definitely your curve nature will be same. Nature of the graph will be same, but it will shift it to the shorter what wavelength. Okay. So children, if you look at this graph again, so this is at a particular temperature T1. But when you move to next temperature T2, which is higher than T1, you can see the nature of the curve is same. But the maximum energy is shifted to the shorter wavelength. So this is the maximum energy emitted at this wavelength, that is called lambda m only, but this wavelength is less than this wavelength. But this is at what temperature? What temperature? T2. And the energy which is obtained at this temperature is also maximum. Similarly, if you go from T2 to T3, when the temperature increases, you can see the shift. Also, the energy, maximum energy obtained is also shifted to the shorter wavelength. So this is the maximum energy which shifted, obtained at this wavelength, and that wavelength also is lambda m. But this wavelength at this temperature T3 is shorter than or less than the other wavelength at other temperature. But still at this we obtain a maximum energy, which means as the temperature of the black body rises, the peak value of the distribution curve, see this distribution curve, the peak value of distribution curve means this value, okay, which measure the what? Radiant energy, which measure the maximum radiant energy emitted by the black body, okay, shift towards shorter wavelength. Yes, shift towards shorter wavelength, because when you move this side, wavelength increases, when you move this side, wavelength decreases. But why the wavelength decreases this side? Because when the temperature increases. When you go to the higher temperature, okay, to measure the maximum radiant energy, and that maximum radiant energy is obtained at shorter wavelength. So there is a displacement of this maximum radiant energy to the which wavelength? Shorter wavelength. So, but this happens at different temperature. This happens at what? Different temperature. Although if you look at the graph, okay, the wavelength is emitted. This black body emit radiation, okay, at that particular temperature in all cases, but only in that particular wavelength the energy emitted become maximum, and that maximum energy can be obtained from a body at a wavelength, and this wavelength is called dominating wavelength. Okay. So children, from this graph, as I said, that as the temperature increases, okay, as the temperature increases of a black body, the maximum energy emitted, radiation shift toward the which wavelength? Shorter wavelength. This means that on heating a body, body to ordinary temperature, heating a body to what temperature? Ordinary temperature. Okay, only long wavelength, means long wavelength is this side. Okay, long wavelength radiation is emitted, because this is a temperature which is less. So when you heat a black body at ordinary temperature, only a long wavelength. So only a long wavelength, okay, radiation is emitted, because that at that long wavelength the energy obtained become maximum. Okay, but as the temperature of the body increases, if the temperature of the body increases, then the radiation again emit, but the radiation of shorter and shorter wavelength, see, shorter and shorter wavelength, okay, will also emit it in increasing quantity. That is why, as you have learned, that you have observed practically also, that when iron rod is heated, when iron rod is simply heated, okay, so, and when you start increasing the temperature, what you observe? When iron rod is heated, first it become what? Light red. It become red. You have seen the color. Then on further heating with increasing temperature, you know the color of the iron rod become orange. After some times, okay, again further heating the temperature, iron rod, the color become yellow, and on further heating it become blue, and at last to a very high temperature, okay, the iron rod become what? White also. So why this rod, iron rod, color changes, okay, and which emit radiation when the temperature increases, is due to the energy, the radiant energy which is obtained, okay, had maximum energy, radiant energy, but at a particular wavelength, okay, and when we go to the higher temperature, when you increase the temperature, okay, then what happened? The radiation, maximum energy radiation, radiant energy which is obtained by the body have a what? Shorter wavelength. That's why, you know, if you look at, if you know that there are 7 colors present in the white light, okay, BIBGYOR. If you look at this color, okay, red is the color which has maximum wavelength. So red is the color which has maximum wavelength. Okay, so if iron rod become red initially at low temperature, so which has a longer wavelength. Once the iron rod becomes, when the temperature of the iron rod increases, okay, then the color of the iron rod become yellow. It become what? Orange first, orange. Okay, because orange, wavelength of orange color is what? Shorter than what? Red color. Okay, that means the wavelength shifted to the shorter wavelength. I mean, this curve shifted to the shorter wavelength. Okay, and after some time it become what? Orange color also, a yellow color also. Okay, and even the color of the iron rod become what? Blue also. Okay, so when the temperature increases, then what happen? The wavelength, okay, the energy emitted by this iron rod, or say considered as a black body, okay, shifted to the shorter wavelength. So this observation was made by William Wien. Okay, and with this observation and the concept of this black body radiation, okay, he got a Nobel Prize also. He got a what? Nobel Prize. So children, this particular scientist called William Wien, okay, made and established a relation between the temperature, okay, and the maximum wavelength obtained from that, or maximum wavelength of that black body. Okay, and this particular relation is expressed in the form of a law known as Wien's displacement law. Okay, so as for Wien's displacement law, the wavelength that is called the dominating wavelength, we also call dominating wavelength, for which E lambda, means this E lambda radiant energy become maximum, is inversely proportional to the temperature. Inversely proportional to what? Temperature. Means from here I can simply say that as the temperature of the black body rises, the maximum energy emitted radiation shift towards the what? Shorter wavelength. More higher temperature has shorter this wavelength, lambda m. Okay, so that the maximum energy which is obtained, E lambda, shifted to the which wavelength? Shorter wavelength. So if lambda m is inversely proportional to 1 by T, where T is the absolute temperature, then we can remove proportion sign to what sign? Equals to sign. So when you remove proportion sign to equals to sign, you have to put some constant, and this constant is given by letter B. B by T, and this B is actually called as Wien's constant. This constant is also known as what? W-I-E-N apostrophe S, Wien's constant. Okay, this is known as what? Constant, Wien's constant. So lambda m equals to B by T is visually a what constant? Wien's constant. So children, we can simply write the relation as lambda m into T is B. As I said, B is called Wien's constant. So the product of the maximum or dominating wavelength of the emitted radiation from a black body into that temperature, at that particular temperature, is always constant. So experimentally, it was found that the value of B, see children, the value of B was found to be how much? 2.9, round up to 1 decimal place, 2.9 into 10 minus 3. Now the question arises, if this is a constant, it has a unit. Now you can easily guess what is the unit of wavelength. The unit of wavelength as a unit is meter, and temperature as a unit is what? Kelvin. So the unit is simply meter Kelvin. So the value of Wien's constant, which is found to be 2.9 into 10 minus 3 meter Kelvin. So this is a constant called Wien's constant. But this value of this Wien's constant say that lambda m into T is always equals to 2.9 into 10 minus what? 3 meter Kelvin. So this can be understood even with the help of graph also. Now this graph, if you look at this graph, you can see that when you calculate the value of this maximum value or dominating value, this lambda m at this temperature T1, the product of these two value will be equals to that 2.9 into 10 minus 3 meter Kelvin. So in the same way, if you calculate next curve, next value of lambda m, okay, lambda m with T2 temperature, the product will be that 2.9 into minus 3 meter Kelvin. So that means in whatever temperature and whatever peak value of dominating wavelength or you calculate, okay, the product always remain what? Constant. So this is actually a law known as Wien's displacement law. Now one of the main advantage of this Wien's displacement law is it is used to calculate. It is used to calculate the temperature of the celestial body, like the temperature of the sun, stars and all. Because this sun and stars are also considered as a black body, okay, which emit radiation. Okay, so with this relation we can calculate the what? Value of this, value of the temperature of the sun also. Now for the temperature of sun, just to tell you that at a wavelength of 4753 Armstrong. So when right from the radiation emit from the sun, okay, reach to the earth, at this particular wavelength, okay, the energy obtained, okay, from the sun will become maximum. That's why this wavelength is called dominating wavelength. So if the energy obtained from the sun become maximum at this particular wavelength, so according to Wien's displacement law, we can calculate the temperature of the sun. But this temperature is the surface temperature of the sun. Okay, that's surface temperature of the what? Sun. So for that, let me just use the formula. If lambda m into T equals to B, then T equals to B by what? Lambda m. Okay, so B value is always how much? 2.9 into 10 minus 3. Now lambda m, okay, is how much? This is for sun. This is for what? Sun. So it is 4753 into, now Armstrong I change it to meter, that is 10 to minus 10 meter. So if you do the calculation, children, like 2.9 into 10 to the power minus 3 plus 10 by 4753 with 2.9 into 10 to the power 7, because 10 minus 3 is 7 by 4753. So if you divide this, multiply this quantity and divide it, you get approximately round up to whole number as 6100 Kelvin. Means the temperature that you obtained in Kelvin scale is 6100 Kelvin. Means look at the temperature, 6100 Kelvin is the temperature of the surface of the sun. Now this temperature we can determine by using Wien's law, Wien's displacement law. That's why one of the main advantage of Wien's displacement law is that we can determine the temperature of the celestial body like sun, stars and all. Okay, so this is how we can explain understood about Wien's displacement law based on the black body radiation and for a perfect black body. Now in the next YouTube video you learn about Stephen's law.